start, I'd like to introduce you to CosmoPower. CosmoPower is a deep learning accelerated framework for Bayesian inference of cosmological parameters. You can find all of the details that I won't have the time to mention in this talk in these two papers written in collaboration with these people. So let me get straight into it. CosmoPower is a suite of neural network emulators for cosmological power spectra, covering both the CMB with emulation of temperature, polarization, and lensing power spectra, as well as large-scale structure with emulation of the matter power spectrum. So let me give you some motivation behind this. The computational bottleneck for two-point statistics analysis of cosmological fields is driven by the solution of the Einstein-Boltzmann equations by means of solvers such as CMB and LSS. This is a well-known problem, and there have been multiple algorithms developed over the years to essentially bypass these Einstein-Boltzmann solvers to compute the power spectrum using, for example, polynomials, Gaussian processes, etc. The motivation behind using deep learning for this is the following. While this is apparently a very simple problem for a deep learning algorithm because the mapping between cosmological parameters and power spectra is very simple, it is actually a deceptively simple problem because if we want to be able to use a tool like this for future next generation survey analysis, the levels of accuracy required to for a tool like this to meet are exceptionally high. And so it makes sense to train an algorithm on as large a set of training samples as possible. And so for this reason, neural networks are particularly well suited to this problem. I would also argue that obviously to gain trust in a tool like this, we need to test it very thoroughly, and in particular test it on a configuration like the one that we expect from future surveys. And the only way to test a tool like this really thoroughly is to perform inference, so to show a comparison of the contours obtained with and without the emulator. I would also argue that in order to solve this problem of emulation of Boltzmann code predictions, we need a flexible tool, meaning that we don't want to repeat the training exercise every time we change any detail in the analysis, such as the systematics modeling, for example. So for this reason, in CosmoPower, for example, we decided to emulate the matter power spectrum rather than emulating the data vector, for example, the lensing cells. But we also split the emulation of the matter power spectrum into an emulation of the linear power and a nonlinear correction. And the motivation behind this is that while we know that nonlinear corrections will change in the future and we will have more accurate ones, so we will need to retrain the emulator on these new predictions, the linear matter power spectrum is essentially known exactly up to numerical accuracy using Boltzmann solvers. So we won't need to retrain the emulator for that case. For the CMB, instead, the key quantities to emulate are the temperature, polarization, and lensing power spectra. So in terms of how the emulation is performed, I won't go into any of the details about the neural network architectures. I should say, because the mapping to be learned is very simple, we don't need any fancy architectures. It's really, we just need a multi-layer perception. But I just want to mention that there are currently two methods implemented in CosmoPower to perform the emulation. One is a direct neural network mapping between cosmological parameters and power spectra, and the other one is a neural network mapping between cosmological parameters and the coefficients of a principal component analysis decomposition of the power spectrum. And the user is free to choose either method. All of the neural networks are implemented in TensorFlow, and the code is completely written in Python. And it's written in such a way that it can really be used as a Boltzmann code without any prior knowledge of machine learning, even for training. Now, enough with the introduction, let me get straight into the results. So I want to start from showing some contour plots from a stage 3 analysis. This is a 3 times 2-point analysis, joint lensing and clustering analysis from the kids survey, 450 square degrees from the kids survey, and an overlapping patch of the sky from the spectroscopic survey gamma. So This analysis using multiness to sample parameter space and sourcing power spectra from class, parallelized over 16 cores, takes approximately 2.5 hours to complete. Whereas with COSMOPOWER, sourcing power spectra from COSMOPOWER, still sampling parameter space with multinest and parallelizing over the same architect or the same hardware configuration, this takes less than 3 minutes. And the contours are essentially indistinguishable, as you can see. Then moving on to more recent data, this is the latest DR4 cosmic shear data release from the kids survey, KIDS 1000. So again, on a 16-core configuration using class for the power spectra and sampling parameter space with multiness, this takes approximately 10 hours to complete, whereas replacing class with COSMOPOWER using the same hardware configuration, this takes less than 10 minutes, and the contours again are essentially indistinguishable. Now, if I were to stop here, this would be essentially a tool used and validated on stage 3 configurations, but so it would be probably useful for other stage 3 analysis, but I wouldn't be able to trust this tool for application to next generation surveys. And so the only way to really test a tool like that is to perform inference on a simulated future configurations, like for example, the one that we expect from Euclid. And this is what it's done here for cosmic shear. Now, apologize for the slightly busy plot, but it is part of the point to show such a large parameter space, because we need to essentially get used to this type of plots as we move towards the analysis of future surveys, and we need to be able essentially to explore very large parameter spaces, which will be required to characterize the analysis of these future surveys. So for this reason, we need very efficient ways of navigating parameter space. And so in this case, using polychord, because the parameter space is a bit larger, and sourcing power spectra from class, parallelized over 48 cores, this inference pipeline takes approximately 6 days to complete, whereas replacing class with COSMOPOWER on the same hardware configuration, this takes only 3 hours. And importantly, there's no need to retrain anything really. All of the plots that I've shown you so far have been obtained using the same emulator for the matter power spectrum. And this is the advantage of using an emulator of the matter power spectrum versus, for example, the lens in CL, so we don't need to retrain if we change survey or we change details of how we model the data vector. Okay, so now another cool thing about using neural networks to produce the power is that, so these are neural networks, so they're fully differentiable, first of all, and then they can also be run on GPUs. So if we're able to rewrite the pipeline, the full pipeline, including the likelihood essentially and the inference engine, in such a way that it can be run on a GPU, then we can really leverage massive acceleration by the GPU. So this is what has been done here. I rewrote the Planck 2018 joint temperature and lensing, temperature and polarization likelihood for TensorFlow. And we also used an implementation of the MC sampler for TensorFlow, so we can essentially run the whole problem on a GPU. And so this problem takes for 150,000 samples using MC and sourcing power spectra from class on an 80-core configuration. This takes approximately 30 hours. Whereas using this GPU sampler and then the TensorFlow likelihood and the emulator, this takes less than 10 seconds on a GPU, which, by the way, if you don't have, you can always go on Google Colab and run it there. And in fact, this is actually one of the notebooks that you can find on the CosmoPower repository. And again, the contours are essentially indistinguishable. So I hope this really motivates the use of these accelerated pipelines for inference. But if this wasn't enough, then really I hope that this last section will convince you. So this is moving now beyond lambda CDM. In this paper with Alessio Spurio, we considered an interacting dark energy model. And essentially we wanted to get constraints on this model from the latest KITS 1000 cosmic shear data. And we wanted to do so using our emulator. Now, so for all the details of this model, I would refer you to these papers where this is described in detail. But from a phenomenological perspective, the only important point is that this is a minimal extension to lambda CDM. It's just a 2-parameter extension. And yet the computational time, as you will see, increased dramatically. So so basically what we did is we trained CosmoPower to emulate matter power spectrum, CMB power spectra, and we used it to get constraints. In terms of the actual constraints on the model, as expected, we did not find any significant constraints on these interacting dark energy parameters. Although, interestingly, we found that if we fix one of them to 1, so basically we go back to a previous version of the interacting dark energy model without a second parameter, we actually do find some alleviation of the tension in the omega m S8 plane. But then if one performs an analysis in terms of chi-square or Bayesian model evidence, we find that this is not statistically significant. And in any case, this wasn't the main point of the paper. The main point of the paper was arguably this one here. So again, this is essentially the same plot I showed you earlier, meaning the same likelihood configurations for a future survey like Euclid, except now we have 2 additional parameters, which are the interacting dark energy parameters. And as you can see on the same hardware configuration, sourcing power spectra from a modified version of class, this problem takes approximately 5 months of runtime. Whereas on the same hardware configuration using CosmoPower, this takes just 9 hours. So I think this really motivates nicely the use of these accelerated inference pipelines, because I mean, also let's be honest, we're not going to run this analysis only once, right? We want to be able to run this multiple times, test different systematics modeling, etc., etc. Okay, so I hope I've convinced you that CosmoPower is a well-tested tool and that provides orders of magnitude speed up. And it's a very flexible tool as well, because this is given by the choice of emulating key quantities, such as the matter power spectrum. Being a purely Python-based implementation can be interfaced with all of the major Python-based samplers, such as Cobaya, Cosmos, MontePython. The GPUs, of course, give you additional speed up, but also very importantly, with CosmoPower, you have a fully differentiable way of accessing the power spectra, which is obviously very important in view of application to gradient-based inference. And then just a few final words on the CosmoPower repository, which is really meant to be pedagogical and as easy as it can, really, in terms of providing an explanation of the different stages of the analysis. So there's not only a full documentation, of course. CosmoPower, by the way, is pip installable, but there are also many notebooks to follow for essentially repeating all of the stages of the analysis, from training the emulator all the way down to implementing it into a likelihood. You can actually run, for example, the Planck TensorFlow-based likelihood and see the contours forming in 10 seconds, and you can compare against Boltzmann codes, etc. And feedback is very welcome, of course, and very much looking forward to receiving some from you. Okay, so that's all I wanted to say. Just to finish off, saying that so with CosmoPower and with the emulation of the matter power spectra and CMB power spectra, we just scratched the surface, really. What CosmoPower wants to become is a fully differentiable library for cosmology, including, for example, emulation of higher order statistics, systematics, and so on and so forth. There's a lot to do, so if you're interested, please do get in touch. And in the meantime, thank you very much for your attention.